Alright, hello everyone. This is Broxgags, and we're making a video here where we're going to discuss a problem in mechanics of materials. I was walking around the square in my hometown. I came across this sign right here on the left hand side and said, hey, that's worthwhile to take a look at. And so we have just a sign. It's got this kind of beam at the lower end here, actually holds the sign up, and then it's hard to see in the picture on the left hand side, but there's actually a wire that's connected right here and then anchored on the side of the building up here. And so the question I'm going to propose is, well, can we find the amount of stress that the wire is experiencing? Just to give us some numbers to play with, I'm assuming the sign weight is 200 pounds. Looking at the sign, that may be a little on the heavy side, but it just gives us a number to go with. I'm assuming a wire diameter of a 1/16 of an inch, and so nice circular cross section here. Just assume it's one solid core wire all the way up. And then I've got a simplified schematic here on the right hand side, just kind of looking at the two-dimensional version of this problem. And so you can see that overall beam's length is 6 feet. The distance between the anchor points of the wall are 8 feet vertically. Basically 6 inches over from the far left end is the first support point or attachment point of the sign, and then the width between those attachment points is 2.5 feet. I'm also assuming each attachment point from the sign to the beam holds exactly half the weight of the beam, so W over 2, or what would be 100 pounds for us. And so the question is, okay, with this loading, what is the normal stress experienced by the wire itself here, which is connecting points A and C. And so first we're going to have to do a little bit of statics, hopefully you can see, in order to figure out the normal stress. I guess even before we get to that though, let's just kind of think of the properties here. Well, I'm saying there's normal stress involved, so hopefully you're thinking sigma for the variable, and formula is F over A at this point. Just a nice direct normal stress application that we have here. So we need to find the force or the tension in the wire itself, and then the area is the cross-sectional area of the wire. And so we know the diameter, we know it's circular, and so we should be able to easily calculate that. And so really we're going to have to use our statics in order to figure out this force. And so to do that, free body diagrams come to mind. And so the free body diagram that's screaming to me is to look at the beam member here, or member AB here, because I do know the force's direction at point A, right? The force has to be in line with the wire itself. A wire is kind of similar to a two-force member, really, except for a wire can't usually be held in compression, right? You take a flexible rope and you try to push on it in compression, it doesn't really support that load at all. And so I should know the direction of the force at A. If I look at B, I'm assuming it's a pin connected there to the wall, and so I'll just have the two components, a B sub X and B sub Y, if you will. Or that'd leave me with three unknown forces in a 2D problem, so we'd work out to be able to solve for all of those forces. And so that'll be our plan of action. We'll get the tension in the wire that way. And so I'll just come down here, FBD, this will be my free body diagram of member AB. And so AB, I'm just going to use a rectangle in order to illustrate that in my free body diagram. There it is. One thing I did have on the left hand side was the tension force. And so we'll make a vector here representing that force. I'm just going to call it T for tension here. And so one thing we'll have to figure out is the direction of that force. We need to be able to break this thing really into I and J components. And so if that dotted line is the horizontal, we need to figure out this angle theta in order to be able to say, hey, T is going so much to the right and so much vertically as well. And then what do we have on the left-hand side here? Or excuse me, the right-hand side. The right-hand side we have pin connection point B. And so we'll take that and illustrate it by a couple of components of the force that it's going to have at that reaction, and we'll just call those B sub X and B sub Y. Really, in the problem that I'm trying to solve, I won't really need to know these, but it's important to have a nice complete free body diagram. And so we're missing one more load, or a couple of forces that are going to be attached, and of course that's the weight of the sign pulling down on it, right? And we've got these two connection points here. I'm assuming those are just going to go straight vertical, and I'll put those in at this point. And so here, Just a nice vertical force at W over 2. A nice vertical force here at W over 2. I'll go ahead and go back to inches now. I think this span was a half foot or 6 inches. I believe the span between the W over 2's here I said was 2.5 feet, and so I'm thinking getting that to inches would be 24 plus 6 or 30 inches here between this span, and then between this span here, between that last force and the pin joint would be this 6 feet or 72 inches minus our 36 inches. Well, it's another 36 inches here. There we go. And so I believe our free body diagram now is complete. One of the things that would be nice to know is that theta, though. We've talked about that in order to fully describe that force vector representing the tension in the wire, or at least the pulling on the beam that the wire is doing. And so let's figure out that angle theta. I'll go back up to my diagram. If it helps, we can put the theta angle here as well to visualize it. Here's the angle theta. Well, you got this nice right triangle forming right here. And so I can just use the inverse tan, right? A tan, if you will, 8 over 6, or 8 feet over 6 feet. And so let's go ahead and knock that out. And so I've got theta is equal to inverse tan. It is opposite over adjacent, so I believe that is the 8 feet vertical height over the 6 feet horizontal height in this application. And we'll figure out what that angle is. Looks like 53.1 degrees. There we go. And so now that I have that angle, I can describe more accurately the force vector associated with the tension in the wire. All good things. And now I'm ready to solve for the tension in the wire, right? We know the angle theta. We know capital W is 200 pounds, so each of these W over 2's are 100 pounds. We do not know B sub X and B sub Y, and we don't know the tension on the wire T there. And so now we're thinking of our statics. It's a 2D problem. We've got a nice rigid body here, we're assuming, and so we'll have 3 equations, right? Sum of the force in the x, sum of the force in the y, and the sum of the moments. Really, if you pick your moment equation right, we should be able to eliminate both b sub x and b sub y and solve for our tension. And so here I'm going to go ahead and jump right to the sum of the moments. Generally, I like to pick the point that I'm summing the moments about is the point with the most unknowns, and so it follows here that that would be point B. So that way I can knock out both b sub x and b sub y from this equation. And so now that I've decided my point, here's my convention. Counterclockwise rotations are going to be considered positive. I can start writing my equilibrium equation. And so here I'll just work right to left. Well, b sub x and b sub y, the line of action of those forces is tracing right through the point that I'm interested in taking the moments about, so no moment arm, if you will, and that goes to 0. Here I've got w over 2. Rotation-wise, it's going to try to go in the counterclockwise motion, so this will be capital W over 2 times the horizontal distance is our 36 inches. And then I have another W over 2. So I work my way to the left. Now we're talking about this W over 2. It's still going to be causing counterclockwise rotation, or a tendency to, and so it'll have a positive contribution to my moment equation. The overall distance, as you can see here, appears to be the 30 plus the 36, or the 66 inches. And then I'm over to the tension in the wire itself here. And so since it is at an angle there, it's not purely horizontal, not purely vertical, I have to think of both the horizontal contributions and the vertical contribution. And so if I can illustrate that a little bit, there's the horizontal contribution, and here is the vertical contribution here. Or if I added these two vectors together, I would get the red T vector here. And so let's first look at the horizontal one. Well, the horizontal one, I've assumed it's in tension, so I'm assuming it's going to the right at this point. Again, I can assume whichever direction I want here. If I get the direction wrong, it'll be just a negative in the magnitude. But I'm fairly confident here it's going to be in tension just because we have a wire here. And so if I look at this horizontal component of the tension vector here, well, it traces right through b sub x there. It's right in line with b sub x. It's right at the point B that we're taking the moments about, and so it's not going to enter into my equation. But the vertical component of the force is not going to trace through the point that I'm taking the moment about, right? The line of action of this force would just be a vertical line right here. Clearly there's a perpendicular offset distance here, and so it would try to create a moment about point B. And so direction here first, well, it's pointed upward, but more importantly for us at this point is that it's going to try to cause clockwise motion, so it'll be a negative moment. And so here I'm running out of room, so I'll just put minus down here. Well, what's the magnitude of that force? Well, it's the t. I don't know the value of t yet, so I'll just represent a variable. T times the sine of theta. So it's my t times the sine of theta here. And then what's the perpendicular distance? Well, that's the entire length of this beam member that we have here, so 72 inches. And at that point, we're almost done with the moment equation. We are assuming this thing's in static equilibrium, and when I walk down the street and look at it, I can't tell it's accelerating at all, so fairly safe to assume that we're in static equilibrium. And so we'll set that equal to 0. And I take a look at my equation I just wrote. Well, W I know is 200 pounds, and the only variable that is unknown is t. So let's go ahead and solve for t. And so I put t right here, t being the tension. What do we have? We've got W times 18 inches plus W times 33 inches all over 72 times the sine of theta. That's 72 inches times the sine of my theta. And now we just can collect our terms, 33 and 18. That is 4351. So we've got something like 51 inches times the W. That was, we said, was 200 pounds is the overall weight of our sine, all over 72 inches, and times the sine of my theta, 53.1 degrees. (51) times 200 divided by 72 times the sine of my angle. 177, we'll call it 0.1 pounds. There we are, 177.1 pounds. And so that's the magnitude of the tension force in the wire itself. And so really what we're finding is the F that I wrote in this formula here. And so with that, we can now find the normal stress. And so sigma is F over A. Here I called this actually T, so that's our tension, if you want to write it up there. Well, the A is just going to be the cross-sectional area of the wire, pi over 4 diameter squared. And so it's 4T all over pi D squared. Just rearranging some algebra, and we'll fill in our values here. 177.1 pounds for the force. Pi, I believe we said it was 1/16 of an inch for the diameter, so we'll square that. And get right around 57,720 is what I have. 57,720 PSI. And I'll put comma T here just to further reinforce that that is in tension. And so there is the result for us. We first used some statics, right, in order to figure out the force that was held inside of the wire itself. At about 177 pounds, and then we know this is a direct normal stress application. One way you could convince yourself of that if you wanted to is to think about this. We got a positive number for this t vector here felt by the beam itself, so that's going to be this one. The wire is actually going to be pulling this way in on the connection point here, and so if I kind of blow up the wire here, well, Newton's third law says we've got an action-reaction thing happening here, and so it's going to feel forces spilling like this. If you look right here at this section here, here's where we have a force perpendicular to the face of the area itself there, which is our normal stresses there. And so in the end we came up with a normal stress of right around 57,720 psi. And so thank you for watching the video. I hope this helps you get a better understanding of normal stresses and also see the importance of statics here, because you can see a lot of our work was a little bit of geometry, some statics, and then finally we got into our bit of mechanics and materials there. And so in later videos I'll probably talk a little bit more about, okay, this 57,720 psi, is it a good value, a bad value? Are we worried about the wire breaking? Also, how long did the wire stretch? Are all different questions that could be asked as well. And so again, thank you for watching the video.